Welcome to This Explainer. Today, we're going to unpack the incredibly delicate, frankly mind-boggling chemical balancing act required to engineer one of the most fascinating high-performance materials on Earth. We aren't just talking about making a simple dinner plate here. We are literally diving into a masterclass in industrial chemistry. All right, let's just quickly run through our agenda for today, which is going to serve as our mental blueprint. First, we'll meet the super ceramic itself. Then we'll look at the manufacturing nightmares, some raw material chemical hacks, taming the mud slurry, crystal phases and firing, and finally, the unbreakable result. So, Section 1, Meet the Super Ceramic, Unveiling Magnesia Porcelain. To kick off our engineering journey, we first need to get a grip on exactly what kind of material we're trying to build. We're looking at a specific category of ceramic that completely pushes the boundaries of material science. Like I said, this is not your average coffee mug. This is talc porcelain, also known as magnesia porcelain. And interestingly, it was originally developed not for our dinner tables, but to meet the incredibly strict insulation demands of high-frequency electronics. Because it has an extremely low dielectric loss, it's just a perfect insulator. Plus, it boasts an intense 87% whiteness and high translucency. So yeah, it's pretty visually stunning too. Now here's where things get wild. 75% of our recipe relies entirely on talc to give the final product its core characteristics. The rest of the mix, just tiny fractions. You've got 10% clay for a little bit of workability, 10% flexes like feldspar to help it melt, and just 5% bentonite to bind it all together. It's an incredibly top-heavy recipe, right? And as we're about to see, relying this heavily on talc, well, it creates massive, massive problems. Which brings us to Section 2, the manufacturing nightmares, a delicate balancing act. You see, producing this material on an industrial scale is just an absolute nightmare. The exact same ingredient that gives it its super strength, the talc, fights the manufacturing process every single step of the way. We're basically dealing with three catastrophic failure points. First, the mud absolutely refuses to bend. It has terrible plasticity, meaning large pieces will literally just crack before they even dry. Second, the liquid slurry randomly thickens, kind of like a culinary emulsion gone horribly wrong, which destroys the flow stability you need for casting. And finally, the firing process in the kiln is incredibly unforgiving, leading to totally warped and deformed pieces. So it begs the question, how on earth do engineers actually tame this completely uncooperative material? The real magic here is figuring out the ingenious chemical interventions needed to fix these fatal flaws before the material even hits the mold. I mean, how do you force a rock that desperately wants to crack and warp into a smooth, flowing, unbreakable masterpiece? Let's find out in Section 3, Raw Material Chemical Hacks, Fixing the Foundation. Okay, so before mixing anything together, engineers literally have to forcefully alter the raw materials right out of the ground. They have to bake the raw talc. This process is called calcination. They roast it at blistering temperatures. We're talking 1350 to 1400 degrees Celsius for 8 straight hours. Why go through all that trouble? Well, raw talc has this greasy, flaky structure that completely ruins water absorption and causes that unpredictable slurry thickening we just talked about. Roasting it destroys that flaky structure entirely, priming it for the chemical steps ahead. Then, to fix the issue of the clay cracking the second you try to mold it, engineers use a highly specific chemical hack. They add barium chloride at a remarkably precise ratio of exactly 3 parts per 10,000. And you have to consider the difference this tiny addition makes. By adding just those 3 10,000ths of barium chloride, the tensile to shear stress ratio of the mud jumps from 0.0318 to 0.0480. In plain English, it instantly fixes the poor plasticity. The material suddenly becomes workable. It literally stops large pieces from fracturing on the factory floor. It is a microscopic tweak, but it yields totally macroscopic results. Moving on to Section 4, Taming the Mud Slurry, Fighting Polymerization. All right, so with the solid clay plasticity fixed, engineers are immediately hit with the next hurdle. Keeping the liquid mud slurry, the stuff used for pouring into molds, from unexpectedly hardening. Production facilities casting this material are bound by a brutally strict thermal limit. The mud slurry must never, ever exceed 25 degrees Celsius, and honestly, it ideally needs to stay under 20 degrees. If the factory floor gets even a little bit too warm, boom, the entire batch is ruined. And these strict environmental rules are absolutely necessary because of these invisible colloidal silica molecules lurking inside the mud. If the slurry gets too warm or if it sits around for more than 7 days, those silica molecules will actively polymerize into thick, useless gels, totally ruining the flow. To combat this, engineers carefully, almost surgically, dose the slurry with sodium carbonate and sodium silicate electrolytes. Oh, and there is one golden, unbreakable rule here. Never introduce calcium carbonate. It acts as a catalyst and aggressively, rapidly accelerates that unwanted thickening. Next up is Section 5, Crystal Phases and Firing, the Microscopic Battlefield. Once the shape is finally formed and dried without cracking, phew, it enters the kiln, and honestly, we can really frame the kiln as a high-stakes microscopic battlefield. Think of it like baking an incredibly sensitive soufflé, except at thousands of degrees. Ordinary ceramics have a fairly wide, forgiving temperature window where they'll successfully bake, but Talc Porcelain engineers, they're forced to operate within a terrifyingly narrow firing margin of error of just 5 to 30 degrees Celsius. If they miss that tiny window, the ceramic will just warp completely out of shape or shatter entirely. Let's look at how this builds as the temperature rises inside the kiln. The heat isn't just baking the material. It's literally forcing the atoms to rearrange themselves. At 600 degrees, the talc transitions into beta metasilicate. Push it to 1,000 degrees and it shifts again, this time into alpha metasilicate. Finally, right around 1,200 degrees, it makes its ultimate transformation into a highly durable crystal called clinoan steatite. The material is fundamentally altering its physical nature, step by step. But creating those clinoan steatite crystals introduces a whole new problem. When they cool down, they desperately want to shrink and shatter. So to survive this radical transformation, those added fluxes we mentioned way back at the start, like the feldspar, they melt into a literal liquid glass. The firing process must generate exactly a 30 to 40% glass phase. This molten glass physically wraps around the newly formed crystals, creating this protective, stabilizing armor. That way, the plate doesn't just self-destruct the second it returns to room temperature. Finally, we reach Section 6, the unbreakable result, data as drama. After surviving the intense calcination, the hyper-precise chemical doping, the incredibly strict thermal slurry controls, and that wild crystal phase shifting in the kiln, we finally get our results. And let me tell you, this intense engineering struggle pays off massively. Across every single mechanical metric, our super ceramic absolutely dwarfs standard porcelain. If we talk about bending strength, it goes up to 1,400 kilograms per square centimeter compared to just maybe 700 for ordinary porcelain. Its tensile strength, meaning its ability to be pulled without snapping, is nearly double. And the contrast in compressive strength is just as staggering. Talc porcelain reaches up to 9,500 kilograms per square centimeter. I mean, this material can handle almost double the crushing force of standard everyday ceramics. Those glass-armored clinoan steatite crystals do exactly what they were engineered to do. When you really understand the extreme chemistry, the sheer blistering heat, and the precise mathematical tolerances required to make this super ceramic, it honestly changes how you look at the physical world. It really leaves you wondering, as we continue to push material sciences even further, what other hidden chemical battlegrounds exist inside the everyday items we just take for granted? Thank you so much for joining me on this explainer. I hope it sparked your curiosity about the invisible engineering happening all around us.